Welcome all of you. In the last class we have been discussing about relaxation. Why last 2 or 3 classes we discussed a lot about relaxation mechanisms, relaxation phenomena. I introduced T1 and introduced what is the concept of T1, especially spin lattice relaxation, how the spins lose energy with the lattice, and what is the mechanism of relaxation, what are the fluctuating fields, what is the frequency of the fluctuating field. We discussed a lot about the spectral density function, correlation time tau c, how they are related, and also correlation time depends upon the size of the molecule. Varieties of things we discussed, and we understood lot about relaxation phenomenon, mechanism of relaxation like dipole-dipole interaction, chemical shift anisotropy interaction, quadrupolar relaxation, spin rotation relaxation. These are the various mechanisms that aid relaxation, especially spin lattice relaxation, which makes the spin to go back to thermal equilibrium. Then I introduced what is called a spin lattice relaxation. I am sorry, spin relaxation, which is again nothing but a dephasing of the magnetization vectors in the xy plane. Bring the magnetization from z axis to xy plane, instantaneously there is a phase coherence. All the magnetic moment vectors are aligned in this particular axis. Bring from exact magnetization by applying a 90-degree pulse from z to let us say x axis. All of them are along x axis, all the nuclear magnetic moments, spins, but because of the local fields, fluctuating fields, the spins will start dephasing. They will lose coherence, phase coherence. Slowly they will start losing phase coherence, go around in the xy plane. And if you take the vector addition of all those things, as time passes by, the intensity of this vector addition of the total magnetization keeps coming down. After a particular time, when the spins completely fan out in the xy plane, there is a complete decoherence, and if you take the vector addition of all these magnetic moments, you will not see any signal. It will be 0, and this is the time which is required for the complete decoherence of the magnetic moment vectors in the xy plane, called spin relaxation time. The time required for that is called spin relaxation time. Okay, that is what I said. Now I also said for small molecules T1 is approximately equal to T2 and all those things. Now we will continue further. Today the longitudinal relaxation causes loss of energy from the spins to the lattice. The transverse relaxation occurs by a mutual swapping of the energy between the spins. For example, one spin in the excited state can come to beta state while another drops to the alpha state. You see, one spin, let us say from alpha come to beta, from beta it can go to alpha. See, it can happen simultaneously. Mutual swapping of the energy between the spins can take place. One spin being in the beta state can go to alpha state, alpha to beta state can happen. This is called a flip-flop process. Flip and flop simultaneously, spins from alpha to can come to beta, then the another spin because of this interaction can go from beta to alpha, and this is why it is called spin relaxation. One spin aiding the other spin to undergo relaxation. This is called a flip-flop process and is called spin relaxation. Okay. Longitudinal relaxation is thus an enthalpic process, whereas transverse relaxation is a entropic process. Please remember, this is an entropic process, longitudinal relaxation is enthalpic process. Okay. And of course you know what is enthalpy, everything you would have understood. There is no point in going to the details of that. Please at least you remember T1 is an enthalpic process and T2 is an entropic process. So now you can work out the decay of the magnetization in the xy plane. You can have two components, sine component, cosine component, and mx and my component I consider, and m0 into sine of omega naught t into e to the power minus t by t2, and my is cosine of, and of course depending upon where you are keeping the receiver. If my receiver is along x axis, then this will become cosine. If the receiver is along y axis, this will become cosine. Does not matter. So depends on our convention. In this case, cosine is receiver is along y axis, this is y axis, and this is x axis taken. So this is m0 is cos omega naught t into t minus t2. This is for my component, this is for mx component. So with a 90-degree y pulse, the magnetization is brought to x-axis. At t is equal to 0, my is equal to cosine of 0. T is equal to 0. So cosine 0 is equal to 1 and sine 90 is 0. So only one component is present, my component is present immediately after t is equal to 0. That means my receiver is along y axis, you get maximum signal. And there is no other component at all because sine 90 is 0. And after certain time what will happen? Other components start developing. They will also start coming up. After time t is equal to 1 by 4, the my component is equal to 0 and mx becomes 1. You can work out from this equation. Very simply plug in the values. It is a simple number, simple arithmetic you can do. And you will see that the e to the power of minus t by t2 represent the fanning out of the each vector in the xy plane. So it decays exponentially. That's what I said. The magnetization along growth along z axis is also exponential. The decay along the xy plane is also exponential. That is given by 1 minus e to the power of minus t by t1, it is e to the power of minus t by t2. It is the decay. Now again put these values here. Let us see what happens if we put t is equal to t2. Now 36.8%. But earlier it was 1 minus something was there. It was 63%. Now it is t is equal to t2. If you put it in here, you will find out it is going to be 36.82. At t is equal to 2t2, it is like the 13.5%. T is equal to 3 times 3 to 4.99. After 5 times t2, it is 0.007. See the total magnetization. If you take t2 is some value, let us say some 2 milliseconds, then 5 times t2 if you wait, after 10 milliseconds, almost entire magnetic moment vectors would have completely undergone dephasing. There is no coherence at all. Though this is almost zero magnetization there in the xy plane. This is again just plugging in the number. I did that. So more about spin spin relaxation. T2. Transverse magnetization start with a particular value, xy and a component denoted as my equal to 0, mx equal to 0, my equal to 0 and goes to 0 with time t2. That is what it is. Initially when it come here, full magnetization, let us say this is my is maximum, mx is 0. After some time you will see that it starts changing. I told you in the previous equation, plug it in, after 1 by 4th of the tau value, then this will become 0, this will become maximum and goes there, it undergoes rotation like this. And then it goes to 0 completely with time t2. So in other word, mx and my can change based on this equation. It is given by mx equal to my equal to m naught e to the power of exponential m naught exponential minus t by t2. This is an equation for measuring t2. Earlier equation was for measuring t1. This is you have to measure mx component or my component, doesn't matter, and this is given by this equation. So t2 relaxation always accompanies t1 relaxation. That is point you should remember. T1 relaxation occurs when a spin exchange energy with the environment, external, that is lattice. It gives to the surroundings. When it exchange energy with the lattice of the surroundings, T1 relaxation occurs. And if an energy, such an energy affects one of the spins contributed to a transverse magnetization, mx or my, then both the transverse and longitudinal components, the angular momentum would be randomly changed. Simple logic, you understand. T1 is an exchange of energy with the environment. Let us say at that time, if one such exchange mechanism affects the spins which is contributing mx or my, xy component, let us say, in which case what happens? The longitudinal relaxation mechanism also affects the transverse relaxation mechanism. Both can take place because some component of the angular momentum gets changed randomly because of this. So T1 relaxation T2 relaxation accompanies T1 relaxation. As a consequence, it will immediately lose phase relation with other spins. So any spin process, any process that causes T1 relaxation also causes T2. That is, T1 relaxation and T2 relaxation processes go together. Any process which affects, gives rise to T1 mechanism causes T2 relaxation also. Okay. This is why it is called T1 contribution to T2 or T1 in T2. It is a word. Remember, this is a definition. T1 contribution to T2 or T1 in T2 means any process that causes T1 also causes T2 relaxation. Now you may ask me a question, can T2 occur? Any process which here we said, any process which causes T1 causes T2. Can there be a T2 process without T1? Can there be a process? All T1 will affect T2, I agree. But can there be without T1? Of course, most of the time T2 relaxation always accompanies T1, but there are one or two examples. Sometimes it can happen, not always. Let us not go into the details of this, because T1 relaxation phenomena is the biggest thing and toughest section to understand in NMR. Lot more to understand, lot more to discuss. We will not go into the details of that. Please understand, it sometimes T2 can also occur without T1 relaxation. That's why then this is called secular contribution to T2. This is a statement I am giving you just to understand. Always in all the books you read, T2 accompanies T1. There are examples. T2 can also occur without T1. That is called secular contribution to T2. When T1 accompanies T1, T2 accompanies T1, it is called T2 in T1. Okay. So now, what is relaxation occurring? T2 relaxation occurring without T1 relaxation. This can happen only because of one form of dipolar interaction called flip-flop interaction. The flip-flop interaction is alpha beta spin go to beta alpha state. Okay. In which case alpha is going to beta, beta is going to alpha. If alpha go to beta, I said flip flop process, one of the spin flipping process. Here simultaneously one is going, other is coming back. Alpha is going to beta, beta is coming to alpha. This is called flip flop process. It's called spin interaction, dipolar interaction, also called flip interaction. This can happen only in such situation. If the pairs of spin simultaneously exchange energy, the longitudinal angular moment like alpha beta to beta alpha states undergoes transition. This results in no change in T1 but causes loss of T2 coherence. It can happen. Remember several phenomena I explained today. T2 always accompanies T1. Any process which affects T1 will also affect T2 most of the time. But there can be T2 without T1. It can happen. One such example is the dipole-dipole interaction where alpha beta changes to beta alpha spin play. This is called flip-flop processes. It can happen. That can also cause. So T1 process affecting T2, T1 in T2. Sometimes T2 can also come without T1. That is called secular contribution to T1. So these are the mechanism for that to occur is flip-flop process. So next question is, T1 is always equal to T2 in solution state, I told you, approximately. And T1 can never be shorter than T2. It is always the case. You will never find situation where T1 is shorter than T2. T1 is always longer than T2 because spin lattice relaxation T1 is very much greater than T2 or approximately equal to T2 in solution state. That is what I said. That means T1 relaxation occurs whenever there is T2 relaxation. Only some processes like flip-flop cause T2 relaxation without affecting T1. And why T1 is longer is simple logic. Unless the magnetization in the XY plane completely undergo decoherence, there is no growth along Z axis. If the XY magnetization, unless it decays, how can it grow along Z axis? So it has to be decay first. So if T2 first completely undergoes this decoherence, after T2 then T1 grows. That's why T1 is always longer than T2. Very rarely you will find situation T1 is equal to T2, but it can happen in most of the time in solution. But by and large, you can always remember T2 is always equal to T1 and T1 is always larger than T2 in solution state especially. Okay. Okay, next we will go further, and this is the graphical representation of the growth and decay functions. T1 is the growth of magnetization exponentially is growing. T2 is the growth of decay of magnetization in the XY plane. This MXY is decays like this. MZ grows like this with this term. Diagrammatically both can be shown. One is exponentially increasing function, other is exponentially decreasing function. exponentially decreasing function is this one. Okay. So now relaxation rates versus time, if you consider, sometimes in some books they use relaxation rates and relaxation time. What is the difference between relaxation time and relaxation rate? Relaxation time is what you are going to measure by doing an experiment. T1 and T2 you can measure by doing certain experiments. I will show you how to measure that now. In this class, if there is time, we will show you what an experiment we do to measure T1 and T2. And these are called T1 and T2 is called relaxation times. If I say T1 is 10 millisecond, it is a time 10 millisecond for the spins to lose energy with a lattice, that is T1. What is the relaxation rate? Rate is inverse of this relaxation time. See, this is denoted by terms called R1 and R2. R1 is the relaxation rate, which is inverse of T1. R2 is the relaxation rate, which is inverse of T2. In some of the biology studies, you can see people will be mentioning the papers and books R1 and R2. R1 and R2 are nothing but inverse of T1 and T2. Please remember this. So now size of the T1 and T2, of course I told you what is a T1, what is the size of T1, approximate value of T1 in solution state. It varies from 0.5 second or very small value millisecond to few seconds we discussed. And of course this is just a general statement. It is not always true. It can vary. It varies from molecule to molecule, spin to spin, depending upon size of the molecule, and of course and where magnetic field you are doing the experiment, etc. So we should have some idea about size of the T1 and T2. T1 and T2 depends upon not only on the size of the molecule but also on the molecular tumbling motion. Two factors depends upon size of the molecule and on the molecular tumbling motion both. So you can see here, this is what we saw earlier. If the relaxation time, if you measure, this is T1 and this is T2. As the molecules undergo slow motion here, T1 is larger. As the motion rate becomes faster and faster, it decreases. In the intermediate region, T1 is very small. Again, when the molecule undergoes fast motion, it goes up. Similarly, T2, it is like this, slow motion. T2 is longer. As the molecule motion becomes faster and faster, T2 becomes smaller and smaller. Okay, this is what it is. So this is slow motion, and this is the fast motion, and this is what the T2 will change. This is how the T1 will change. So when the molecular motion slows, T1 shortens and T1 again increases. For small rapidly rotating molecule like free water, T1 and T2 are very long. So these are the important things, we should know that. In reality, the signal decay is faster than the normal T2. See, we say signal decay in the XY plane, that is a T2. But is it comes only because of the spin-spin relaxation mechanism? Are the two spins exchanging energy? Is that the reason why it is decaying? There could be various other factors which contribute for this. For example, there could be magnetic inhomogeneity, magnetic field inhomogeneity that can contribute for the spins, that can also give fluctuating field at the side of the nucleus, that can cause dephasing. In reality, the signal will decay faster than the normal T2 because of various other parameters. So the actual T2 what you measure is not the real T2, is not a normal T2. So that is why that this is called effective T2, called as T2. T2 star, I am sorry, T2 star is called effective T2. So this T2 is a normal T2. Then how do you get the normal T2 when you know a T2 star? T2 star is always less than T2 because it decays faster because of external phenomena. If there is less external phenomena, if there is no disturbance from the other magnetic field inhomogeneity, etc., then what will happen? At the most T2 star can be equal to T2. It can happen. Otherwise, generally T2 star is always smaller. So then how do you find out what is T2 star? It comes from various inhomogeneity of the magnetic field when you put a sample in a magnetic field. So but generally T2 star is obtained by given by equation called 1 over T2 star equal to 1 over T2 plus 1 over T2 I. Okay, so these are all the contributions from various things. What you measure is the T2 star, and the actual T2, this is inhomogeneity contributions. T2 I means contribution coming because of other inhomogeneities of the magnetic field. So, real T2 if you want to calculate, you should know T2 star and you should know this thing, or you should at least eliminate this term to get real T2. Okay, so this is the diagrammatically this what happens for the nuclear spins. See, you bring the magnetization to xy plane, see what is happening. As it comes down, it is dephasing in the xy plane, it is coming down in the intensity, simultaneously it is going up. You see the thing what is happening, the magnetization you have brought back to xy plane, and then immediate at any given instant of time, immediately as soon as you bring it, the magnetization is maximum, and at any given instant of time signal keep on decaying in the xy plane and goes along the. See this way, unless it decays completely it cannot go along z axis. That is why I said T1 is always longer than T2. So this is a phenomena simultaneously happening, look at it, while decaying it is also growing simultaneously. This is a simultaneous phenomena. If you visualize the process of T1 and T2, actually this is how it sees. We should visualize the process. It appears as when it is decaying like this, simultaneously it is going up and up. It is like a spiral. If you visualize this thing from the top, here it is decaying in the xy plane, simultaneously it is going up. It is like you have an umbrella closed and hold invertedly. Now keep on opening the almirah. Let us say I open the almirah first. Take an almirah, completely open it, spread it along xy plane. Now that means the magnetization has brought the x axis, and now slowly I am closing the almirah, closing the umbrella. This component on the xy keep coming down and grow, it will start going on z axis. The vertical component of the umbrella starts going up. Initially it will be spread here and slowly start closing up, open and close. It is like fanning out of the nuclear spin when the umbrella is open. Is when the umbrella is completely closed, then what will happen? Magnetization is growing along z axis. Exactly phenomena, but it goes like this. It keeps reducing like this, like this, like this, like this, and grows. This is a spiral. This is a like as if spiral is going with intensity coming down the xy plane, simultaneously growing along z axis. This is how both the phenomena are simultaneously happening, and that is how we have to visualize T1 and T2. In brief, we have discussed a lot about relaxation concepts, relaxation phenomena, etc. Now let us take some summary of these things and then go for measurement of T1 and T2. In brief, remember, relaxation is a radiationless transition. It will not give rise to signal detection. It will only aid the spins to relax, to decay in the xy plane and grow in the z axis. We saw it corresponds to energy states of the spin and the lattice. Spin in the upper state of the spin the spins come down, and then energy from the spins in the lattice in the lower state will go up. Spins in the upper state will come down, lattice will go up. All those exchange phenomena is going on. But then remember, it is not giving rise to creating magnetization for detection. It is a radiationless transition. So relaxation is a radiationless transition. Now what you call longitudinal spin relaxation, it is called T1. It is nothing but the recovery of the magnetization, establishment of thermal equilibrium of populations, and it is the exchange of the energy between the spins and the lattice. And the various phenomena for this thing we discussed. Again transverse are the spin relaxation T2. It is a decay of transverse magnetization in the xy plane, and here there is no exchange of energy of the spins with the lattice. It can only one spin causes the other spin to undergo dephasing. Okay, this and then if I look at the NMR spectrum very clearly, looking at the width of this peak, I can get the rough estimate of the spin relaxation. The spin relaxation is nothing but the measure of the line width. See, this is the line width of a spectrum. I know what is the line width, nu half. If I know the width of the full width at half height, nu half, this is equal to 1 over pi times T2. So if I take a spectrum, measure the line width here and take 1 over pi times that line width, 1 over pi times that line width, then you are going to get T2 approximately. So rough guess is you can measure the spin lattice relaxation time by knowing the line width. Very easy, very straightforward way of measuring T2. But of course, it's approximate value. If you want to measure accurately, you have to remove field in no measurable contribution, etc. There is a complicated experiment one can do. We will come to that later. But this is, you should remember, in case if you are going to get a very broad signal, obviously it means that T2 is, when the signal is very, very broad, this will bring it down, this will go up, T2 will be very short. The spins are relaxing very fast, dephasing very fast in the XY plane. As a consequence, you are going to get a very, very broad signal. T2, very short T2 means broad signal, very broad signal. This is the important thing you should know. Okay. Now we will go into the measurement of the relaxation times T1 and T2. How do you measure these two relaxation times? So far conceptually we understood. Approximately we measured what is T2 by looking at the line width. Fine. But we have to precisely measure T1 and T2 accurate values. How do we do that? So before that I wanted to tell you, I told you T2 is the measure of line width. Now the line width is what? It is because of the free induction decay, time domain signal. In the Fourier transformation we understood time and frequency are inversely related to each other. You know, they are related by Fourier transformation. If the signal is decaying very slowly in the time domain, it will frequency is very, very sharp. If the signal decays very fast in the time domain, signal will be very broad in the frequency domain. This is in the Fourier transformation. When we introduced the theory, when we understood a lot about the Fourier transformation, you please remember we discussed these things. So now look at a signal like this. I have two FIDs. This is a rapidly decaying FID and you get the short T2. That shows it is decaying very fast and the spins in the XY plane has dephased very fast. That is called short T2. Short T2 means the spins are dephased very fast in the XY plane. Look at this FID. This is a long decaying FID, slow decaying. It takes more time to decay. Then it is a long T2 and short P. So longer the time the spins takes to decoherence, undergo decoherence in the XY plane, sharper the lines you are going to get. This you should remember. So that is why looking at the free induction decay you can understand what is the line width. This way I said T2 is a measure of approximate line. Line width is approximate measure of T2. So now how to measure the T1? First of all, simple mechanism, put a sample in this magnetic field, wait for some time to see the signal. Then as soon as you put the sample, keep on pulsing rapidly, very, very rapidly. It is a very, very difficult thing, you cannot do it till you see maximum signal. It is practically very difficult, you do not know, you can't do the pulsing so fast and you do not know when you have reached the maximum signal, how much time it takes like that. But that is one way. Other way out is disturb the spins in the thermal equilibrium, apply radio frequency pulse, bring the magnetization from Z axis to X axis, you have perturbed it and then design an experiment to see how much time it takes to go back. See, that is the simple experiment. Disturb the spin system, bring the magnetization to X axis or Y axis. Now it has to go back. Design an experiment to measure the time it takes to go back to Z axis to achieve thermal equilibrium. It has to recover as a function of time. Measure this time. Measure the time it requires to go back to Z axis. Then you will understand, you can measure what is the T1. T1 is a measure of time which is the decay of the magnetization, growth of the magnetization in the XY plane. All I do is a simple experiment like this. It is called there are 4 or 5 different experiments to measure. Progressive saturation, saturation inversion, or null method or inversion recovery method, varieties of experiments are there. I am not going to use the details of all the different experiments and you can choose the experiment depending upon the T1 or whether your sample is a longer T1 or a shorter T1 etc. But basically commonly used experiment is inversion recovery experiment for measuring T1, especially in solution state, which are short T1s, not T1s of the order of days and hours. You cannot do that. There is a different method for that. But in most of the time in solution state where the T1 and T2 are of the order of few milliseconds or seconds, you can use an experiment called inversion recovery sequence and measure the T1. So, it is a very simple 2 pulse sequence. First pulse is the 180 pulse and second is the 90 pulse. And then initially before application of the 180 pulse, all the spins are in thermal equilibrium. Give enormous time, give a delay, make sure that spins attain the thermal equilibrium, and then apply a 180 pulse. What does 180 pulse do? Bring the magnetization which is along z axis to minus z axis. It will tilt by 180 degree. Then give some delay and then apply 90 degree pulse and start acquiring the signal. Now what you do is, don't do one experiment, keep on varying the delay. N number of experiments we have to do. Every time vary the tau delay and measure the signal and measure the intensity of the signal. And then use this different intensity obtained for different tau values and then correlate it and then fit it to a function. Relaxing, there is a function which I told you, mz equal to m naught equation, mz equal to m naught into 1 minus e to the power of minus t by t1. Fit it into that equation, you will get the t1 values. It is a very simple thing because you know tau, you know the mz, and you should know what is the equilibrium magnetization. Equilibrium magnetization is something, the system has attained thermal equilibrium with full magnetization is available, and then keep on varying the delay and see that intensity initially it will be minus z, starts growing slowly, and after a certain time it will again come back to m naught, mz minus mz, it will become plus mz, which is nothing but equilibrium magnetization m naught. Then at different tau values you measure the intensity of the peaks, fit it into this equation, you can measure the T1 accurately. So 180 pulse, invert the spins, m is always longitudinal, no transverse and no signal initially. So largest deviation of the equilibrium can be achieved by the first RF pulse. Bring the magnetization to this thing, largest deviation you get signal. The spins recover towards equilibrium position by losing their energy, start going back. And then, okay, this is what I have to discuss, something more about what happened to magnetization after spin dropping I have to discuss. I will come to that later, but remember one thing, an experiment we can design, but we have to disturb the spin system by applying a 180 pulse, bring the magnetization to x axis or y axis, whatever it is, depending upon where you have receiver, and then first 180 pulse, bring the magnetization to minus z axis, give a delay between 180 and some delay, apply another 90 pulse, another 90 degree pulse, and start collecting the signal, monitor the intensity of the signal as a function of tau value, then measure this, and the number of experiments if you do, you fit it into the equation which is mz equal to m naught into 1 minus e to the power of minus t by t1, then you can measure the accurate value of t1. So what is happening when you apply 180 pulse? There is what we have to understand by what is called a term called spin dropping. I will come to that, I will discuss that in the next class. So I will stop today, but today anyway we have understood lot about spin relaxation also. I told you about what is a spin relaxation, mechanism of spin relaxation, and we discussed and said the relaxation is a radiationless transition. In the case of spin lattice, there is exchange of energy between the spins and the lattice, and it attains thermal equilibrium. In the case of spin relaxation, it is only between the spins. There is no exchange of energy. Spins lose to coherence because of one spin interacts with the other spin because of flip-flop process. One spin can disturb the other spin. Everything happens, both spin relaxation T1 and T2 happens because of fluctuation in the local field. And T1 is a growth along z axis, T2 is a decay along xy plane. Both are exponential. And then we understood how to measure the T1. Simply you have to measure the T1 by inverting this magnetization from z axis to minus z and see how it grows as a function of time. For that a simple experiment can be designed which is called inversion recovery experiment. 180 pulse tau 90 pulse experiment you have to do and measure the intensity of the signal as a function of tau delay and fit it into the growth function mz equal to m naught into 1 minus t by t1. That is what we do to get the t1 and how do we do the experiment, what happens when 80% T2 will measure. Quickly we will finish this in the next class, and with that we can go to another topic later. For NOE and other things we will discuss. Okay. So I am going to stop at this stage. We will see you in the next class. Thank you.